Hey YouTube, what's up? That's Link. Welcome back to another episode of Coding Session, and this is my problem of the week from the Leetcode Weekly Digest. It's another binary tree problem. It's called the Univalued Binary Tree, and the problem simply states a binary tree is univalued if every node in the tree has the same value. Return true if and only if the tree is univalued. As you can see here, all these nodes are the same value, but this one has a 5 in it, and that's false. A couple constraints: the number of nodes in the given tree will be in range 1 to 100, and each node's value will be an integer in the range of 0 to 99. So not really serious constraints we don't have to worry about too much. Now, a couple of videos ago, I went over the depth-first search algorithm, and since we're dealing with a binary tree, it's a little bit different than a graph. Why? Because nodes in a tree may contain many cycles or edges, and the node may be visited twice, 3 times, or 4 times. Notice, for example, node 2 has 4 edges. It has edges 1 to 2, 0 to 2, 2 to 3, and 2 to 0. That is 4 edges, so it can be visited up to 4 times. Now, binary tree is just like this. You got a root, and then it connects to the left and the right. They chain together like that. So you're just going to be visiting it once in a sense, versus a graph a little bit more complicated than a binary tree. So I went over the popular traversals with the binary tree in a couple episodes ago, in order, pre-order, and post-order, and these algorithms are based off the depth first search algorithm, or the idea of depth first. You go as far as you can before backtracking. There's many ways to do this, which is in order, pre-order, post-order. In order, you visit the left, then the root, then the right. Pre-order, you visit root, left, then right. And then post-order is left, right, and then root. Now, there's another traversal we haven't gone over. I will probably go over it in a future episode, and that is called the level order tree. Think of this as a printer, or you're typing on Microsoft Word. You start all the way at the top and you go left to right, and when you're at the end of the line, you go back down and you just go back to left to right again. It's 1, then 2, then 3, then 4, then 5. But once we visit 1 here, we're visiting 2, but then we're jumping all the way back and then visiting 3. So breadth first search or level order traversal is based off the breadth first search algorithm, breadth first search idea. Simply as it says, we're going by levels, and breadth first search pretty much states we're visiting a current root's neighbors, which is tree node left, tree node right, before moving on to the next subtree. Now 1, 2, and then jump all the way back to 3. And then 4 and 5. You can see how this could cause a little bit more performance issues, because we're going 1, then 2, and then we got to jump all the way back to 3, which is not 2's right, but 1's right. Versus depth first, we're going all the way as far as we can before backtracking and visiting other nodes. So depth first search is faster than breadth first search, and in your data structure classes, you will go over all these 3, but you're mainly going to be going over the depth first traversals, which is in order, pre-order, and post-order. So that is the difference between depth first search and breadth first search. I will do a video, like I said, on level tree order traversal, which is the breadth first search algorithm, when I can. So stay tuned for that. But we're going to go ahead and apply the depth first algorithm here, and we're going to do the pre-order traversal, which is root, left, right. Now, this was my second take on the video. I had a disruption, so I actually have something here, an instance variable, and that will be a list data structure of integer, because we're going to be creating another function here, which is our depth first search method. Function, method, both the same thing, but most common you're doing Java, these are methods, but it's a function. and we're going to name it vals, and then we're going to assign it with, so instant dated it, and then vals is equal to new array list, assign it with array list object reference. And this is polymorphism at play here. We've went over polymorphism in our OOP concepts video. And then I wanted to start to write our depth first search method. So public void DFS, and we're going to want to take in a tree node object reference. We'll just call it node. And if the current node we are on is not equal to null, meaning it's an actual tree node, has some data into it, has a left and a right, we want to simply add the value of that node to our array list of vals. So node.val, as we can see here in the definition of this problem's tree node, node.val, right here. And then we want to start the recursion, node.left, DFS, node.right. Pre-order right here, you're visiting the root, the left, and then to the right. Now, we want to start the algorithm, the depth first search, with just root. And root is the tree node object reference parameter in the method signature of is Univalued tree. And then we want to, after the algorithm has done and we've added every single possible node's value into our array list, we want to iterate through this array list and identify if this is a univalued tree. We can do this with an enhanced for loop. So for each int I is equal to vals, and I already went over the whole for each thing. This is really what it is in Java. For int, whatever you want to call it, in this case I, in whatever list you're iterating through. But I like to call it for each. That's what we use in C# for each. And that's how I always read an enhanced for loop, because it's just easier for me to read. So for each int I and vals, it's just a little bit easier for me to read. Maybe for you too. I don't know. Just thought I'd mention it. So for each int I in vals, if the current value we're on in our array list vals is not equal to the first value in our array list, which is the first that the root of the tree, the very first root of the tree, all the way in the top here. So if the current value in our array list that we're on is not equal to the value of the root of the tree, very, very top root, we want to return false, because that breaks the univalued rule. The tree is not univalued, and there's a different value than all the other nodes. Otherwise, we want to get out of this for each loop and just return true, because we want to just verify if the current value we're on is equal to the root of the tree's value. So I is not equal to vals.get for first element in the list, 0, return false. Otherwise, we will return true. So let's run our code. I spelled something wrong. Node. Let's try running this again. As you can see, the first test case passes. We will submit other test cases, and there we go. Runs 0 ms faster than 100% of the Java submissions online. I actually didn't expect this. So that is the univalued binary tree problem on Leetcode, and also just a comparison between depth first search, the depth first search algorithm or the traversals versus the level order traversals or the breadth first search algorithm or traversal. I will make a video eventually on level order or breadth first search. Probably the next episode. Right now I'm a little busy in my schedule right now. This is the only video I could make this week. So yeah, hope you guys enjoyed it. Thank you guys for watching. If you need if there's anything unclear, leave a comment down below. I'll try to explain it the best I can and help you out in any way I can. Thank you guys for watching, and have a nice day.